problem 2400, number of ways to reach a position after exactly k steps. So we are giving two positive integers the start position and end position, and initially you are starting at a position with the start position on an infinite number line. So initially we are starting at here the start position. So with one step, you can move either one position to the left or one position to the right. So let's just use an example. So the first example, the start position is 1, it is here. So for one step, we can go to the left, we can go to the right, or we can go to the left. So this is the end position, so it is a 2. And this case just means k steps. We need exactly k steps to finish from the start position to the end position. So for example, let's just use one case. From 1 to 2, this is one step, and 2 to 3, 2 steps, and then 3 to 2. So this is one of the methods. So another way is 1 to 2, 1 to 2, yeah, so 1 to 2, and 2 to 1, 2 to 1, and 1 to 2. So this is going to be the second way. The third way is 1 to 0, and 0 to 1, and 1 to 2. So this is going to be the third way. So in total, there are going to be 3 different kind of ways. As you can see, it seems it's like it's like some kind of enumeration or some kind of brute force. Yeah, so the idea is that definitely we're gonna start from the start position. So for example, this is the start position 1, and this is the end position 2. So definitely we're gonna start from the start position, and then we're gonna use the brute force to attack to the left or to the right. Yeah, and if we are at this position, we're gonna try to go to the right or go to the left. Yeah, it means from here it seems it is a sub problem. Yeah, it seems this is a dynamic programming. So from here, we have 2 different ways, and then if we go to here, we still have 2 different ways, but we just need to count how many steps. So we need to have for this example, we need to have 3 steps. So if we used all the 3 steps and our end position is 2, so definitely we're gonna count it as 1, and then we're gonna check all the possible cases. Yeah, so we can directly use dynamic programming to solve the problem. Let's prepare a mod. It's gonna be 10 to the power of 9 plus 7, and we're gonna use a cas, and we're gonna define the function with f. So we're gonna call the function, and inside we're gonna prepare a start position, because this is important. We're gonna start from this start position, or you can start from the end position, it doesn't matter. And then we're gonna use this value k. It means we're gonna have k steps. So inside, let's just prepare a position and with the step. So what are we gonna return? So definitely we're gonna return all the different cases. So position, it can go to the right side, and then we use the one step. And another way is we can go to the left side, and still we used one step. And in total, it's gonna be modular on the mod. So let's just put them together. Yeah, and what are going to be the as cases? So the as cases is that if the step equal to 0. So this means we used all the steps, and then we're going to check the position. If the position equal to the add position, so we're going to return a 1. Otherwise, we're going to return a 0. As you can see, this is going to be the solution for the problem. It is not so difficult. We just need to find the variables we need for the dynamic programming. It's going to be a position and a step. Now let me just run it. What is wrong? I'm gonna check the position. If it is yeah, because there's a typo, let me just make it right. So it's gonna be a return. Yeah, now as you can see, it works. As you can see, it passed for all testing cases, and I think this is okay for solving the problem. And let's just try to do some trimming for the binary tree. Yeah, because according to our idea, so for example, if we were to reach from like 1 to 2, And what about this k? If we go too far away, so for example, this is a number. Yeah, let's just use the right side. Maybe this number is gonna be too far away. Maybe this is 5. So if this is 5, and the value, this k, maybe currently, let's just check. Maybe this k is 2. Yeah, so our precision is 5, so the step k becomes 2. Can we reach this number 2? Definitely it is not possible, because if we go to the left, it can go to 5 to 4 and 4 to 3, but we can never reach 2. So it means if it go to the left or if it go to the right, if it goes too far away, definitely it is not possible. So we're going to prepare some edge cases to trim the binary tree. So yeah, so if the absolute value of the precision minus the add precision is too far away, this means it's going to be more than the number of k. So k steps just means after k step we can reach a maximum to the left or to the right with this kind of distance. It's going to be a k step. Yeah. So if it is more than, so if the distance is more than k steps, definitely it is not possible. So we're gonna return 0 to trim the tree a little bit. Yeah. Now let me just submit it. Yeah, as you can see, it also works, but it didn't improve the speed so much. But this is okay. Definitely, we did some trimming for the binary tree for the recursive function. I think that's let's just check the time complexity. So the time complexity is the precision times the step. So the precision gonna be the start and add precision. So basically it's gonna be 1000, and the step is this value k. It's gonna be 1000. So the time complexity gonna be 1000 times 1000. Yeah, because here for this precision, it can go to the left or it can go to the right. Yeah, but even it can go to the left or it go to the right, it cannot be a really big value. Yeah, because the step gonna be 1000. Even it go to the left, it can only go to 1000 steps, and even it go to the right, it can only go to 1000 steps. If it is 2000, it's also a small value. So 2000 times 1000 is gonna be the final time complexity. So this is still okay. Yeah, I think that's all about this problem. See you next time.